Okay, here we go. We're going to continue on with trying to find different ways of finding antiderivatives. And as I mentioned at the end of the last last video, we're going to do something which allows us to find an antiderivative of that. So let's get right on it. Notice that it's the product of two functions. And so the method we're going to use for that, which is we use typically whenever we have the product of two different kinds of functions. Notice that this is an algebraic function. It involves x's, and this is an exponential function. Okay, so we have the product of two different kinds, and here's the method we use. And this method is called integration by parts. For those who like the kinds of mathematics where you just kind of do rules and just plug in, this is your kind of mathematics here, okay? You have to recognize to use it, but once you do, it's a nice little formula. And the proof is so easy that I'm going to get the formula by actually proving it, okay? Every author that you'll ever see when they talk about integration by parts, they always call the functions u and v for some reason. I don't know how that started historically, but I'll do the same thing. So suppose you have two functions, u of x and v of x, and suppose we take the derivative of that product. Well, you know how to take the derivative. What's the derivative of the product? It's the derivative of the first, so I'm going to write it like this: du dx times v plus u times the derivative of the second, which is dv dx. Agreed? So there it is. And now I'm just going to rearrange things. Going to bring this over to, well, actually I'll bring leave this where it is and bring this over to this side. So I'm going to have u dv dx is equal to the derivative, I'll just write the derivative of u times v minus, I'll write it as v times du dx. Agreed? I'll just switch the order of that. And now this is a function, this is a function, and this is a function. And since they all are functions of x, let's go ahead and take the find the antiderivative of each. Okay, the antiderivatives are going to vary by a constant, so we can do that. So we have this whole thing. I always have to throw on the dx right there, and we also have this thing right here, and we can break it up and write this thing right here. And if I thought ahead a little bit more, there we go, like so. So we just take the antiderivative of each, and let's see what happens. So here I'm going to write this as the antiderivative of u. Now you're used to this from doing with substitution. I can think of taking the derivative of a function times the dx as just the differential dv right there, right? You're used to, here's u, and u is equal to x cubed. And so du is equal to what? The derivative of this thing, 3x squared dx. So when you take the derivative times dx, you get this thing. It's formally what you do by just bringing the dx over. And so those things can cancel out, or you can just think of dv. What is dv? It's the derivative times dx right there. Okay? So that's that right there. And similarly, this thing right here is going to be v du right there. And here you're taking the antiderivative of the derivative of something. And when you take the antiderivative of the derivative, you just get that something back. So that's going to be uv. And so right there is the formula for integration by parts. Okay, I'm going to write it up here. I'm just going to write the down just a little bit. the integral of u dv is equal to uv minus the integral of v du. And I guess you can see that. Yep, make sure you can see that. There you go. There it is. And that's the formula for integration by parts. And let's see once now how we can use that. Okay, just like substitution, there's never any guarantee. It's not like you're taking the derivative where you just follow the rule and you're guaranteed to get the answer. Here you give it a try. If it works, fine. If not, it doesn't work, okay? So let's give it a try. So here's the way you do it. You take part of this thing, one of these functions, and you designate it as your u, and you designate the other one as your dv. So let's go ahead and do it. Let's take u is equal to x, and then I will write dv down here. Dv is going to be equal to e to the x dx. So there's the dv. So notice that that's your u and your dv, and so now we have to find these other things. Well, let's see. If this is u, what's du going to be? Then du is going to be 1 dx. It's the derivative of that thing, which is 1 dx. And here, notice I have to take the antiderivative. If the derivative, if dv is equal to e to the x dx, then what would v be? Well, it's the antiderivative of e to the x, which is easy enough. The antiderivative of e to the x is just e to the x. So you have that right there. So what does integration by parts formula say? It says that the integral of u dv is equal to u times v. Well, here's u times v right here. X times e to the x. And then minus the integral of v du. So here's v and here's du. If I take this and multiply it by this, I'm going to get e to the x times 1 dx. And so these two things are equal, which means this is equal to this. And the value of using this method is if you end up with an integral there that you can, an integral here that you can actually integrate, you can actually find the antiderivative, whereas you couldn't do this one. Yeah, you can in this case, right? We know it. This is going to be x e to the x minus, what's the antiderivative of e to the x? It's just e to the x. And then finally you throw on your c. So there it is. There's the answer. There's the antiderivative of this thing. And if you ever want to check it to make sure you're right, let's just say check it here. Let's take the derivative of x e to the x minus e to the x plus c and see what happens when we take the derivative. Well, let's see. First of all, I have to use a product rule here. Product rule says you take the derivative of the first times the second minus the first times the derivative of the second. The derivative of e to the x is e to the x. And then finally, what's the derivative of this thing? It's going to be negative e to the x. And the derivative of c is 0. And what do we end up with? Oh, this should have been a plus here. Okay, right? The product rule says the derivative of the first times the second plus the first times the derivative of the second. And then finally, here we go there. And notice that these two things go away, and you end up with your x e to the x, which is what we wanted. So there it is. That's called integration by parts. Okay? Integration by parts. So, if you're thinking about this as we do it, one question that comes to mind should be, well, how did you know to let this be the u and this to be the dv? So let's do it the other way and see what would have happened if we would have done it in the other direction. We could have set u, let's see, where did I do it? I guess I did it over here. So u is equal to e to the x, and dv is equal to x dx. Okay, the dx always goes with the dv. So what's du going to be then? So then du is going to be the derivative of this thing, which is e to the x dx. And here we would have to take the antiderivative. So the antiderivative of x is going to be 1/2 x squared. Agreed? So what does the integration by parts formula say? This is one you should just memorize. The integral of u dv is uv minus, you flip them around, minus the integral of v du. So this is going to be uv, so it's going to be equal to 1/2 x squared e to the x minus the integral of v du. So v times du is going to be 1/2. You can bring that out front if you want. 1/2. Here you're going to get an x squared e to the x dx. So what did we learn? This is a valid formula. We used integration by parts. This antiderivative, this is equal to this. It's perfectly good. It's fine. It's everything except helpful, right? We started off with a function where we had an x there. Now we've dug ourselves deeper. Now we have a function with an x squared there. So it's certainly correct. It's just not helpful. So they're both correct. We want the one that helps us out. So there you go. So then you ask, well, which one helps you out? Well, first of all, you can try it both ways to see if either one helps. There's nothing wrong with just experimenting and trying. You can put a little bit of thought into it. Okay, if you put a little bit of thought into it, you realize that by letting u be equal to x, du is equal to 1 dx. So I knocked down the power. I made this one simpler. Whereas it didn't matter whether dv was equal to e to the x dx, then v was equal to e to the x. That didn't change. See that? We didn't make that one better or worse, but we made this one simpler by going from there to there. So that's one thing you should have in mind is, let's try to make it simpler. Okay? So, what if instead of having an x there, we had an x squared there? How would that have changed things? Let's give it a try. So let's do the same idea I had before. Let's try to make things simpler by letting u be equal to x squared and dv be equal to e to the x dx. Okay? Then du is going to be 2x dx, and v is going to be e to the x again. Okay, so let's see what we get. So this is going to be uv, here's your uv, x squared e to the x, minus the integral of v du. Here's your v, here's your du, your 2 can come out front, and your v du is going to be e to the x times, I brought the 2 out front, let's put the x in front. Like that. So you look at that and you say, well, that's fine and dandy. Problem is I still have something that I can't find the antiderivative of. That might be your first thought. Hopefully your second thought is, hey, we just found the antiderivative of that. Agreed? That's the one we just did. So what was the antiderivative of that? Shoot, I shouldn't have erased it. Let's see, I forgot what it was. I think it was x e to the x minus e to the x. Wasn't that it? I believe so. Okay, and you can say plus c. The point is, if you take your c and multiply it by 2, you're still going to have another constant. So that's the idea. Okay. So the point is, you might have to use integration by parts more than once. Okay, can you imagine what if you had a 20 there rather than a 2? You'd have to go through this 20 times, and it becomes a bookkeeping problem. Just making sure you put this in for this whole thing right here. That's why it's kind of nice to factor the 2 out front. I can just pop that right in there. Here's your final answer. X squared e to the x minus 2x e to the x. And then minus to minus is going to be plus 2 e to the x. And then finally plus c. And I'll leave it to you, the viewer, to go ahead and take the derivative of this thing. You're going to have to use a product rule there. You're going to have to use a product rule there. And by the time you're all done, you should end up with that again. Okay, there you go. Let's try another one. Let's try x times cosine of x dx. Okay, I'm going to do it similar to the previous one. I'm going to think, well, let's see. By letting my u be equal to x, then du is equal to 1 dx, so I've made that one simpler, whereas the dv is going to be cosine of x dx, and so v is equal to sine of x. Agreed, sine and cosine are one is no worse or better than the other, so I haven't made anything worse by going from here to here, but I have made things better from going from there to there. So what's the antiderivative? It's uv. Oops, I'm thinking about my next problem. Minus the integral of v du. v du. v du is going to be sine of x. Did I do that right? uv minus the integral of v du. Yeah, that's good. And now you can finish it off. You write that as x sine of x minus, what's the antiderivative of sine is, the antiderivative of sine is the negative cosine. So by the time you get rid of that negative, it's going to be that. And there you go. By the way, if this were a definite integral, say we went from 0 to, I don't care, 0 to say pi over 6 right there, okay? Then all that means is that this whole thing here, you integrate, you evaluate this from 0 to pi over 6, and this would go from 0 to pi over 6. And you can do them separately or you can do them all together. If you do them all together, you're like this. So if you put in 0 and pi over 6, there's no reason to have a c there. You might as well just let c be 0 in that case, because any constant is going to just cancel itself out. 0 to pi over 6. And so what happens? You put in a pi over 6 here, you're going to get pi over 6 times the sine of pi over 6 is 1/2, plus the cosine of pi over 6 is square root of 3 over 2. And then what happens when I stick in a 0? Here I'm going to get 0 times 0, and here I'm going to get a 1. So there's my final answer. Okay? Pi over 12 plus square root of 3 over 2 minus 1 as your final answer. Okay, see, it's kind of nice. This is fun stuff to teach. It just works out really slick. Okay, well, so I've done things like that. Let's do some other ones. Okay, let's try, here's one of my favorite ones. Well, I tell you what, before I do that, let me give you the hint. This is a hint that my graduate topology professor showed me. I taught his class for him one day when he was sick, and he said, okay, you're going to be teaching integration by parts. He was Korean, and he said it was a little, not broken English, but it wasn't his native language. And he said to me, he says, you know late? And I said, what are you talking about? He says, late. And he wrote late like this. And he said, this is how you know what you should let your u be equal to. Okay, what choice should you have for u? You go down the word late, and whatever the first thing you come to is, that's what you let u be. So what kind of different functions are these? L stands for logarithmic. L stands for algebraic, things like x, x squared, things like that. T, what's that going to stand for? That's trigonometric. And that we've already used the last one is what? Exponential. Right? Pretty cool. It just happens to work out that way. Let me make sure that everything is still being watched by you. Okay, very good. Okay, so there it is. And so I'm going to mention that before doing this next one. Here we have the ln of x dx. Doesn't seem to be in the right form. I only have one function there. The whole point of integration by parts is to use two functions and such. And so you look at that a little while, and then you have a little stroke of genius, and you say, wait a second, I can put in a second function. I can just put in the function 1. 1 times that. Agreed? 1 times that works. And now 1 is an algebraic. It's okay. 1 or x squared, those are all algebraic. So what does integration by parts say to do? You let u be equal to, I go down this in this direction, and so I always take the log before the algebraic. So this is going to be the ln of x, and dv is going to be your 1 dx. Okay, so what's du now going to be? It's the derivative of this thing, which is 1 over x dx, and v is the antiderivative of 1, which is x. Agreed? Remember, you always throw your dx in with your du and your dv. Okay, this is a case where you just need to be careful. Have you heard the old saying, cleanliness is next to godliness? There's really something to be said for that. I remember watching the movie, if you haven't seen it, the movie Dead Poet Society, where at the beginning of the movie they show a trig teacher, and he's talking very sternly to these high school students and saying that precision in trig is so important. And I always kind of shuddered at that when I first watched it, but as I've taught more and more, I realized he was really onto something. He could have been a little friendlier as he said it, but being precise, being careful, that's a huge part of being successful in mathematics. So anyway, here we go. So the antiderivative is equal to what? It's u times v. So there's u times v. By the way, notice that if I had set dv equal to this, I would have gotten stuck right there, because I don't know what the antiderivative of ln is. That's what we're trying to find. So really the only choice was to make it go in this direction. So here we go. It's u times v, which is going to be x ln of x, minus the integral of v du. So here's v du. You're going to get x over x is 1 dx, and now you can finish it off. X ln of x minus x plus c. And again, every single one of these, you could go ahead and just take the derivative of this again and see that you get that, and you're better, okay? Otherwise, the whole world is going to start crumbling because this is all wrong. Okay, assuming I didn't do anything wrong. Okay, very good. So there's a good one. Let's try another one. I'm doing all my favorites here. Let's do this one. Okay, there's our first one that doesn't have an algebraic. It has a trig and an exponential. So let's follow the rules and see what we get. So I'm going to let u be equal to the trig, which is sine of x. And I'm going to let dv then be equal to the rest of it, which is e to the x dx. Look good? So u is always equal to the first one you come to as you start from the top and go down. So that's that. So du is going to be cosine of x dx, and v is going to be e to the x. So here we go. So this is going to be equal to uv, which is e to the x sine of x, minus the integral of v du. So here's v and here's du. It's going to be minus the integral of e to the x cosine of x. dx. Agreed? V du. Well, shoot, you look at that and you say, that's no better than what we started with. I had to find the antiderivative of this thing, and now I have to find the antiderivative of this. It's 6 of one, half dozen of the other. What should we do? Well, kind of like the x squared e to the x, give it another try and see what happens. Okay? So now let's go ahead and find the antiderivative of this one. So I'll do the same thing as before. I'll go down this rule line here. Oops, I guess I should have just left this. And I'm going to let this be the u be the trig function. So that's going to be cosine of x. And then du is going to be minus sine of x dx. Agreed? So this is where you have to be careful. So watch me carefully here. I'm going to leave the negative out front, and now I'm going to put a big bracket there. Okay, this bracket is going to be just this thing right there. Okay, you got to be careful, especially if you have negative signs or 2's or something else out here. Be really careful. Okay, so now what's the antiderivative of this? It's uv, which is uv is going to be e to the x cosine of x. I'll write them in that order. Minus the integral of v du. So here's my v, here's my du. It's going to be e to the x. Here's my du. Notice I have a negative there, so I'm going to bring that negative out front and cancel it with that one. Sine of x dx. Okay? And now I can apply this negative through all the way and get e to the x sine of x minus e to the x cosine of x. And then the minus also applies to this, minus e to the x sine of x dx. Okay, are you encouraged or discouraged? Look at here, we did it twice, went through all that work, and this is what we're trying to find the antiderivative of, and we ended up with that again. It looks like a terrible cycle here. This isn't looking very promising. There's an old story I remember hearing about this the shoe salesman that was sent to the deep dark jungle of wherever, and he writes back to his company in Europe and says, hey, no market here, no one wears shoes. Okay, all the aborigines, the natives, no one wears shoes. And so they took him home, and they brought another salesman and sent him there, and he wrote back after a week, sent him a telegram and said, hey, great market here, no one has shoes. Okay, so what seemed to be a terrible thing ends up being a positive thing in this other guy's eyes, and that's exactly what's true here. Okay, you look at this and you say, this is terrible, and all of a sudden you get yourself a little insight and you say, hey, let's just add this to this side. See this? If I add this over, I'm going to have two of these things. So I'm going to get two of these. E to the x sine of x dx is equal to e to the x sine of x minus e to the x cosine of x, and then plus c. And then you just divide through by 2. And I'll just divide them each through by 2 like that. C over 2 is still 2, so you can get rid of that. And boom, we're all done. Isn't that clever? Very clever, very clever. So, so there's our answer. Okay, so that one worked. Okay, well, let's see. There's all sorts of them to do here. I don't know really where to stop. There are a lot of nice problems with integration by parts that you can do. Some of these we will do a little bit later on. Maybe I'll just mention this one to you. There's something called a reduction formula, where you basically you do this. Let's just do it real quick. I guess as long as I mentioned it. Okay. If you have that, I guess I'll get rid of this now. We know it. Now we will let u be equal to x to the n. Du is equal to n times x to the n minus 1 dx. dv is equal to e to the x dx. So v is equal to e to the x. So if you use this, you're going to get u times v is going to be x to the n e to the x minus the integral of v du. And notice I can bring the n out front again. And I'm left with x to the n minus 1 e to the x dx. And can you see why that's called a reduction formula? You have an integral which you write in terms of something plus another integral. But the point is this other integral has a reduced power from the one you started with. This is n, here's n minus 1. And so this is called a reduction formula. So if you could use this over and over again if you wanted to, instead of if you had x to the 10th power, you wouldn't have to keep doing it over and over again. You just use this formula and you say, well, x to the 10th power, let's do it for the 5th. What would you get? So x to the 5th power e to the x dx is equal to what? It would be x to the 5th times e to the x minus 5 times x to the 4th e to the x dx. And then what do? Then you take this thing right here, and again the bookkeeping is really important, and you say, what's this equal to? I'll kind of abuse the notation here and say this is equal to what? The reduction says, formula says that's x to the 4th e to the x minus the integral of 4 times x cubed e to the x dx. So you can just keep doing it until you get down to our original one, and that's how you'd finish. So you don't have to go through the process each time, you just use the formula. Okay, there's just one more I'm going to do. How about this one? What about let's take it x times the arctan of x dx. Okay? This is the only one that doesn't fit into this pattern. Oops, not that pattern. Late. Okay, you might be tempted to say that this is a trig function, but it's not. It's an inverse trig function. So this isn't absorbed by that. This one doesn't, the word late doesn't apply to. However, if you just put any thought into it all, you realize you don't have any choice. We don't know what the antiderivative of the arctan is, okay? We don't know. We do know what the derivative is, so that's really our only choice. So we can let u be equal to the arctan of x. And the derivative, which we learned back in Calc 1, is equal to what? 1 over x squared plus 1. So there, and then dx. Agreed? So there's u du. And now what's the rest of it? It's going to be what? Dx, or dv rather, is going to be x dx. And so v is equal to what? It's going to be the antiderivative, which is going to be 1/2 x squared, period. Okay, there's u, there's du, dv, and v. Okay, so what does the integration by parts say? It says uv 1/2 x squared arctan of x minus the integral of v du. So what's v du? It's going to be right here. I can bring the 1/2 out front. It's going to be x squared over x squared plus 1 dx. Okay? So what can you do there? Well, let's see. First of all, this looks a little more promising than this, but we still need to find the antiderivative of that. This is actually one that we're going to be spending more time on in a couple sections, how to find antiderivatives of rational functions. A rational function is some function involving just powers of x divided by another function, but one polynomial over another polynomial. So we'll learn how to do it later, but let me show you how to do this particular one. It's just kind of a clever trick. Okay, you have this thing right here. Okay, that's what we're trying to find the antiderivative of. And here's what we're going to do. We're going to force the top to look like the bottom. So I'm going to add 1 and subtract 1. You agree I can do that? I just added 0. So now this whole thing right here is just a 1, and then I'm left with minus 1 over x squared plus 1 dx. Agreed? And now, do you see the answer to that? The antiderivative of this is x, and the antiderivative of this is arctan. Agreed? Antiderivative of that is arctan plus c. So here you go. It's going to be 1/2 x squared arctan of x minus 1/2 of this. And again, I'm going to stick this whole thing in right here. So 1/2 of this is going to be minus 1/2 x, and then also minus 1/2 arctan of x. And then finally, a c times a negative 1/2 is still a c. So there you go. Very good. So now you know. Now you have all the necessary things to know for integration by parts. And it's a really nice method. You should try a bunch of other ones on your own. There are a lot of different ones. By the way, here's just one more that comes to mind. Suppose you have something like this. Okay? How would you do that one? Well, I'll let you think about it. You should think about it before you go on. But here's what I would do. First, make a substitution. And so the whole point of this is it shows that sometimes you have to start using a couple methods together. So make a substitution. Now, normally when I make a substitution, I use u for the substitution, but I don't want to use u now because I can kind of see ahead in my mind that I'm going to be using u as part of my integration by parts. So I'm going to let t be equal to x squared. So dt is equal to 2x dx. Agreed? So now this thing becomes e to the t. Now what? I have to get a I have to get a dt in there. So that's the next thing on my mind is I have to get a dt in there. And the dt requires an x. See this? So I have an x cubed there. I can think of that x cubed as being, let me just keep that where it is and write that as x squared times x. Agree that x cubed is equal to x squared times x. So here's an x dx. X dx is equal to 1/2 dt. See that? So x dx is equal to, bring the 2 over, is equal to 1/2 dt. So 1/2 dt is equal to x dx. So now I've taken care of this, and I've taken care of that x right there and the dx. I've got rid of all that. Now this will work as long as I can get the rest of it in terms of t, which I can. Notice that t is equal to x squared, so there I have that. And now it's just the problem that we've already done. What's the antiderivative of this thing? I think it was t e to the t minus e to the t, right? Plus c. There you go. So there you go. Okay? I'll leave you with one final one to do. This is one of my favorite problems. Try to do this one on your own. E to the square root of x dx. Okay? If you've been trying your mathematical muscles at these other problems, give this one a try, and see once what you can get. Okay, very good. That'll take care of integration by parts.